All right, so now that you understand the concept of an antiderivative, in this section we're going to start looking at how to take antiderivatives of actual functions and not just finding antiderivatives from the graphs and interpreting it conceptually. So what are we asking? An antiderivative is just asking what is f of x the derivative of, okay? And the symbol that we use to for the antiderivative is, it looks a lot like the integral symbol, right? You can see this is basically our integral symbol, the summa, only it doesn't have limits of integration. There's no a to b, right? It's not a definite integral, so we call it an indefinite integral. Let me get rid of that because there's no a to b. It's called the indefinite integral, and so this is the symbol that we use to indicate that we're asking for the antiderivative. So in this case, this particular antiderivative is just asking what is f of x the derivative of. Okay, so we've got a derivative of, and we're asking, okay, what did that come from? What function did that come from? And just like in the warm-up, you saw in the warm-up to the last lecture, we can get a function, but then it's really a family of functions. So for example, if I said what's the indefinite integral of 2x dx? Okay, there's no limits of integration. All I want is the antiderivative. And you know that it had to have come from something like x squared. But, like I said before, it could have come from x squared plus 1, or x squared plus 40, or x squared minus 62. You know, so it could come from a whole family of functions. So, because 2x is essentially the slope of the function, and if we add a constant to it, it doesn't change the slope of the function. So, the antiderivative of 2x is actually x squared plus c. Okay, so the indefinite integral of 2x is just asking, what is 2x the derivative of? And we get a whole family of functions that would satisfy that question. All right, and so just like when you learned how to do derivatives, we have a whole bunch of indefinite integrals or antiderivatives for common functions, okay? And they come directly from the derivative rules that you learn. For example, the power rule. We know that the derivative of x to the n is equal to n x to the n minus 1. So basically, if we're going in reverse, we have this situation. So the integral of x to the n dx, right, the indefinite integral, antiderivative of x to the n is x to the n plus 1 over n plus 1, and then plus c. Okay, and you know, if you're computing antiderivatives with indefinite integrals, you can always check your work, because if you take the derivative of your result, you should get, if I take the derivative of this, I should get that. And I can do that with the power rule. So if I took the derivative of that, you know, I'd get 1 over n plus 1 times n plus 1 to the n plus 1 minus 1, and you end up with x to the n. Okay, so we're just doing derivatives in reverse. And all of these derivatives, or antiderivatives or indefinite integrals of common functions just come from the derivative rules that you already know. I think the main exception here is this one, the antiderivative of 1 over x. Now you know that the derivative of natural log of x is 1 over x. So you would expect that the antiderivative of 1 over x would be the natural log of x. But the problem is that the domains are different between those two functions. So the domain of 1 over x is basically anything but 0, right? We can put in negative numbers, but we can't put negative numbers into the natural log, right? Because the natural log has a base of e, any power of e is a positive number, right? So, but we can integrate 1 over x, right? We could integrate 1 over x and get answers for negative values. So in order to make this work, we have to it's the antiderivative of 1 over x is actually the natural log of the absolute value of x. And that's important. So don't forget your absolute value signs, because that's the one that's really the most tricky to understand. I don't want to go into details, but I'm actually going to post a Khan Academy video where he explains why that is in a little more detail. But I'm not going to go into detail here. So you should recognize, all of these as being kind of the reverse of the derivative rules that you already know. Okay. There's also some properties of antiderivatives, properties of indefinite integrals. For example, if you the antiderivative of the sum of two functions is just the sum of the antiderivatives. Or the antiderivative of the difference of two functions is the difference of the antiderivatives. Okay, and again, that kind of just follows straight from the derivative rules that you already know, as well as this other one where we have a constant times the function. So the antiderivative of a constant times the function is the constant times the antiderivative of the function. And it kind of makes sense just based on what you know about the derivative rules. Now, that's about all I'm going to tell you about this. You've got some rules or some common integrals of common functions that are given here, and then it's just a matter of practice. That's really what it's all about. I believe there's quite a few problems in this particular homework assignment, and it's just because you need to practice. It just takes practice. So this lecture is going to be, I've 7 minutes now, and I've probably been too long-winded as it is. But like I said, it's all comes down to practice now. So let's do some antiderivatives here, some examples. Now it's too bad that I can't see both of these on this same screen. But if we want the antiderivative of 8x cubed plus 1 over x, okay. The 8 is just a constant, so I'm just going to write that. And then I want the antiderivative of x cubed. So it's x to the n plus 1, right, over n plus 1. Okay. And then, okay, so this is just a sum. So the antiderivative of a sum is the sum of the antiderivatives. So I'll just put a plus there. And we know that we can just look back at the table I just showed you. And the antiderivative of 1 over x is the natural log of the absolute value of x. Okay, and we cannot forget to put plus c at the end. So that's the antiderivative, but I could simplify that a bit. Let's make it 2x to the 4th plus the natural log of absolute value of x plus c. Okay, and that's all there is to it. Just follow the rules, get used to using them, and you'll be fine. So let's do another example. All right, so we've got, we want to find the antiderivative of 12e to the 0.2t. Okay, so we have a constant. I'm just going to write that down. And then our k, in this case, is 0.2. So the antiderivative is 1 over 0.2 e to the 0.2t, and then plus c. And if I simplify that, I get 60 e to the 0.2t plus c. All right, just practice. That's all it takes. All right, I'm going to do, see, I told you we're going to have a really short lecture here. Here's another one. This one involves sine and cosine. All right, so we've got a sum. So we're just going to take the antiderivative of a sum is the sum of the antiderivatives. So I'm just going to integrate these one at a time. So the integral of sine, can look that up, is equal to negative cosine of x. Okay. And then, okay, I have a constant. So I'm going to put the 3 down. And then I've got cosine of 5x. So I've got to take into account the 5 there. So you get 1/5 times the sine of 5x. Okay, and then plus c. And that's it. I mean, there's not really much I can do to simplify this. I could combine this into into one 3/5, but that doesn't really make a difference. But 5x plus c. Okay. All right, there you go. 10-minute lecture, right? And other than that, it's just practice. Just practice, just practice, just practice this. So I will post the solutions to the practice problems on Canvas, and we'll talk to you later.